In this lecture, we're going to talk about radiation exposure, obviously with a focus on exposure for humans. So let's start with just how we measure radiation. Um, there's kind of two general ways to measure it. You can either measure the emitted particles or events per unit of time. So like how many times is a nucleus decaying to something else and emitting a particle? Or you can look at the amount of energy that's being given off by a sample or really absorbed by something in the surroundings of that sample, like a person. And so here are a lot of different ways of measuring or units that are used to communicate the amount of radiation that is someone's being exposed to or something is being exposed to. So Curies end up in that first category we talked about. So a Curie, named after Madame Curie, is an exposure of 3.7 times 10 to the 10 events per second. So events are going to be emitted particles, something that would be like a count per minute or count per second if you had like a Geiger counter. And so that's really talking about a rate of activity, like how many of these things am I being exposed to, of these particles over a period of time of 1 second. And then we kind of start looking at different types of units that really communicate what's being absorbed by a body or by an object. And so a gray, which is a GY, is the abbreviation, is measuring the amount of energy that's going to be absorbed by a body or like some tissue from radiation. And so it's going to be in units of joules per kilogram of body tissue would be 1 gray. So here's our conversion rate here. And so that's going to depend on the size of the object. It's going to depend on the amount of particles that are being emitted and the amount of energy that they have. So it's not just how many of these nuclear decay reactions are happening, but what type of particle and what energy are they producing emitted particles at. And so then we have the rad, which is a great name, right? So the rad also measures the amount of energy absorbed by tissue, and it's just kind of on a different scale. So it's really 1 rad is 0.01 grays. So it's kind of like, if we use the analogy of the metric system, it's going to be like 100 times a gray, right? So we have kind of a simple conversion there on a different scale. Then we have RBE, which is Redogen Equivalent Man. Oh, sorry, that's REM. So RBE is really a biological effectiveness factor. So it itself isn't actually a measure. But what we do is we multiply an RBE times a rad. So we take these two together. And that's what our REM is. So REM is a Redogen equivalent man. And what we're tracking with REMs, which is the most common way I've seen radiation exposure discussed when talking about humans, is it's not just the energy that is being absorbed by the body tissue measured in rads, but then it is also corrected by a biological effectiveness factor that's going to take into a lot of different variables that affect the severity of an exposure event. And that isn't something that we'll cover in this class because it's kind of outside my field of expertise. So those are a bunch of different ones. Now, the standard units, the SI units for radiation are sieverts, SV, which is really equal to 100 rem. And so these are our primary units that we're going to use, rem or sieverts, when we talk about radiation exposure. All right, so this is, I want to do a quick comparison between radiation exposure for like average person back in 1987, so when I was a little kid, and to about 2006, so when I was a young adult. And it's changed, like where we're getting radiation from has really changed. Back in 1987, about 81% of the radiation a person was exposed to was from a natural source, and only 19% of it was man-made. And so looking at this pie chart, who doesn't love a pie chart? you can see that like the main contributing radiation source to like our overall exposure within a year was from radon, which again is a byproduct of uranium decay, and it kind of seeps into from the ground into houses, usually collecting in basements. The other really big ones were, cosmic radiation and terrestrial and internal and medical X-ray radiation accounted for a lot. By comparison, I just want to point out nuclear medicine here at 4%. So when we compare here. So then now let's look at 2006. And it's changed drastically. Now, only 50% of our radiation exposure in the year is coming from a natural source, and 50% of it is man-made. So look, our radon has dropped down to just 37% of the exposure you're likely to get in a year. And what has really increased is nuclear medicine. Look at that. Now it's 12%. So, and then just other forms of medical radiation now are all the way up to 24%. So we still have like our background, space, internal background, terrestrial background. And now it's just a smaller piece of the pie because we've actually increased the amount of radiation we're being exposed to. And just coming back to nuclear medicine, there's a 7-fold increase I forgot to mention. And this is ionization or ionizing radiation, so things that'll actually break down tissue and different molecules when it hits it, rather than just energy. And so that's a pretty big shift in like our daily lives throughout a year, and a really big shift in our exposure to radiation. So kind of talking about this some more, let's talk about some of the kind of average radiation doses in the US that you're being exposed to. And so we're going to look at these at millirems per year. So it's a rem, but like 1,000th of a rem over a year. And so looking at things like cosmic, just radiation that's coming in from outer space, like just hitting the Earth's surface, or radiation that's coming up from the soil, or radon. Radon's still the big one at 229 millirems per year. But then kind of like these cosmic, terrestrial, and internal ones are all pretty small. And internal, we mean these are just radioactive isotopes that just naturally exist in our body, right? Like carbon-14 or potassium-40. And then if we look at our man-made ones, none of these really actually are as large as the radon contribution that we see right here. But the biggest one are CT scans at 149 millirem per year dose. And then nuclear medicine and just general medical applications are pretty high. And so that's bringing us up to about a 620 millirem exposure every year on average. Let's compare this, and if this helps. So the dose limit from Nuclear Regulatory Commission licensed activity. So running a nuclear reactor. So if you're if you work at a nuclear reactor, it's been decided that your annual dose as a worker at a nuclear regulator is going to be 5,000 millirems per year. That's a lot compared to the 620 that we just calculated for an average dose for a person throughout the year. And again, a lot of these high doses are going to come from things like CT scans or whole body CT scans, or even higher. So here's the average American dose is 620 right here. And so if you have to get a whole body CT scan, that really increases your actual exposure over time. But in the grand scheme of things, it's nothing like working at a nuclear reactor. So there's that. I'll point out transatlantic flight down at 2.5. All right, so here are some more examples of radiation doses people are exposed to, just to give you more context for this. You can read through these on your own. I'm just going to point out a few. So kind of looking at that transatlantic flight. So 5-hour airplane ride, you're at 2.5 millirems per trip. So small, but there you go. Another one that I find interesting is So we have all of our medical ones, of course, that are increasingly higher and higher and higher, with just like a chest ray at the smallest, and then your dental X-ray getting up to 30 to 80, and then at the high end, a thallium heart scan. And then I like looking at the consumer products too, because if you look at it, just being in a building for a year, like just existing around buildings, it's actually a higher dose than a transatlantic flight. So like a 5-hour jet ride. Your watch is not really contributing very much, but tobacco products is a lot, 16,000 millirems per year. And I will say, the last year when I did my, and this is why smoking is bad speech around it, I had several students raise their hand and say, like, no, come on, that's 30 cigarettes a day. That's a lot. Like, that's actually just a lot. I mean, that's not your casual smoker. But it's still, there's a fair amount of radioactive particles you're exposed to, along with the carcinogens. So there's also a real difference in how your body responds to acute versus chronic exposure to radiation. So an acute exposure would be like a really high level of radiation over a really short period of time. And when that happens, it's going to kill a large number of the cells. This might be from a nuclear blast or being exposed to a reactor core. And this is going to just weaken the immune system, lower the body's ability to absorb nutrients from food, and you can actually result in death, right? And so an acute exposure, usually people are going to end up dying from infections as those tissues have been attacked. Now, a chronic exposure is something that's going to be a low dose of radiation over a period of time that's much longer. And the effect of this is going to be an increased risk for developing cancer. So the radiation, especially ionizing radiation, is going to damage DNA. And if it's not properly repaired, so if a lot of damage is happening over repeatedly, we're not going to be able to repair it all. And that's where we're going to get the development of cancer cells. They might also damage reproductive organs. So you see sterilization in people with chronic exposures to low doses of radiation. And you might also then see genetic defects in the offspring as well from someone who's had a chronic exposure. And so thinking about some of the effects and the actual dose and kind of putting some numbers to this, let's look at just radiation dosage. Which is going to have the effect of it's so like you're hit by this high energy, but then also the emitted particles are going to have an ionizing effect that are going to ionize to break off electrons from different molecules, which the effect of that is that it breaks bonds, right? And so it can tear apart like molecules in this way. And then that high amount of energy transferred into cells will also just damage these large biomolecules and or cause them to just malfunction within the cell. And the ionization can do that as well. And so thinking about our doses in REMS in an acute exposure, if you had a 20 to 100 REM dose, and remember all of the ones we were talking about before when we were going through 5,000 dosage or 1,000, we were talking about millirems, right? So now 5,000 millirems is that maximum amount for your exposure if you're working at a nuclear plant. So now multiply that by 5 and you're at 20 or 4, and you're at a 20 REM dose. So anything above 4 times what you'd be exposed to at a nuclear reactor on a regular basis is going to lead to a general decrease in your white blood cell count, and you're going to have a cancer risk. Then if you go even higher, so now you're getting a 100 to 400 REM dose, you're going to get radiation sickness. You're definitely going to have an increased cancer risk as well along with that. But if you get above a 500 REM dose of radiation, you will die. So that's kind of giving hopefully a little bit of benchmarks to set when we think about and talk about radiation and whether or not it's dangerous and what our exposure is. Because the idea of radioactive particles and exposure to radiation, it's scary, but also at the same time, there's like a level of context to this that you're constantly being exposed to it. Like your body has radioactive particles in it. And it's really that dose and the quantity that makes it scary or just completely, totally normal. All right, so here are some of the biological effects of a radiation exposure. And just some points on it. I'm going to kind of go through. So first of all, the more energy the radiation has, the larger the effect will be. And we talked about our different types of emitted particles have different levels of energy to them, where our gamma radiation is at a really high energy level and our alpha radiation is at a low energy level. And so then also the more ionizing a radiation is, it'll have a larger effect. But that has to depend, that also depends on its ability to penetrate into human tissue. And so your gamma particles will penetrate more, but ionize less. And our alpha particles will penetrate less, but they'll ionize more. And so there's kind of that balance there. The radioactive half-life of the radionuclide is also really important. If it's a short half-life, the exposure overall will be shorter. Whereas if it's a longer half-life, it'll continue to do damage for more time. But while we think about the half-life of the particle, there's also a biological half-life for any element. And so let's say I ingest a radioactive isotope for a treatment or for a diagnostic test. Let's say it's going to stay in my body for a whole month, except my body will also potentially be flushing it out. So as your body is removing that particle just through metabolism, through your body and through the waste streams out, then you can actually be reducing the concentration of that radioactive element in your body faster than just its half-life or decay. And so a biological half-life might actually be shorter. Of course, if it is something that ends up in your body, it might not be. If it stays in your body doesn't have a very easy mechanism for getting it out. The physical state too is important. Think about this, like if it's a solid particle that's like standing there that won't get into my body, that's one type of radiation. But if it's something like tritium that's in my water, then it gets into my body and it becomes part of me. It's like mostly water. And so that physical state can have an impact too. If it's a gas and I inhale it, and I can't really get away from that the way I would a solid. So here's just a few ways that we detect radiation. I think the most well known is a Geiger counter, and the imagery of the Geiger counter clicking and buzzing as it detects radioactive particles. And it's really counting the electrons that are generated as you ionize argon gas. And so as that radioactive or that radiation interacts with the argon gas, it ionizes it. And those electrons as it's ionized are what the Geiger counter is going click, 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 click and counting. So film badge dosimeters are usually used you'll put them, like clip them on you on your jacket, or you'll put them on your wrist or something like that. And that's really using a photographic film to detect radiation, and as it detects more and more, it'll show that dosage essentially through kind of the effect of it on the photographic film. And we also have scintillation counters. These are counting the number of flashes of light per minute that result when radiation hits a chemical. And so it's going to excite electrons out, and you'll see flashes of light, and that's what it's detecting. So it's detecting light rather than detecting electrons, like in the Geiger counter.